the screen. So I'm Vikash Mansinghka. I'm delighted to be here. And I feel really fortunate that my talk is right after Dan's, because I'm going to be giving a complementary story to the foundational story he presented. So we're going to be working into probabilistic programming from the frame of application systems that are aiming to augment human intelligence. And the context I'd like to set for that, there's, of course, been a tremendous amount of excitement over industrial AI systems, especially recently. But the problems that those systems solve are all games that kids can learn to play. So they have very narrowly defined sets of rules. It's easy to tell who's winning or who's losing. And while it may be hard for a kid to get as good as a top performer, it's easy to get them to play the game. And that flexibility is, of course, incomprehensibly vaster than the flexibility of the AI systems, right? Like AlphaGo can't parse English, let alone play Jeopardy.
I'm not sure if you have kids, but things are not as easy with kids.
Yeah, I don't mean to say that any kid can trivially learn how to play chess or Go or Jeopardy, but over many ages, And another feature of all of these domains is that the nature of human knowledge that's needed to do well on them, especially the classic games, is quite circumscribed. And I want to contrast that with the types of problems we've been working on from an applied perspective. So my lab's been working with the Gates Foundation for a couple of years, trying to help them do empirically grounded policy advocacy in their malnutrition practice. The Gates Foundation funds primary data collection and a network of partners that represent many different fields of expertise. And questions they're interested in include questions like, well, let's say they fund a malnutrition intervention in Bangladesh. Should they try to pitch a particular government in Africa to adopt the results? Are the results relevant? On what basis? What if they're costly to adopt? So, how to make an empirically grounded case. And these are really difficult problems. There are no well-defined rules. There's clearly data that's relevant. There's also a lot of human knowledge that's relevant. And something that was a surprise to me as a computer scientist interacting with these communities is that the state of understanding is quite loose right now. For example, when it pertains to growth stunting due to malnutrition, so will a child have, an abnormal growth trajectory due to growth insults in early childhood? Kids that have actually similar nutritional environments have very different outcomes. So it's not just as simple as give everybody, more food overall. I'm going to be returning to this problem over the course of the talk. So the technical tools we've been bringing to bear on problems like this all come from probabilistic programming. And for the purposes of this talk, the frame I'd like us to adopt for what probabilistic programming is an emerging field at the intersection of modeling and inference, programming languages, and system software, where probabilistic programming systems, unlike traditional programming languages, like C, let's say, but a little bit more like languages like, let's say, SQL, let you put in modeling assumptions and ask questions. But unlike languages like SQL, they let you get back answers that may be incomplete or uncertain. And sort of over the course of development of the field, many different types of languages have been proposed and prototyped, growing from the lens of either basic AI research or statistical relational learning or statistics in some cases, a bunch of different user communities. I'm mostly going to be focusing on Picture and BayesDB, which are two domain-specific probabilistic programming languages under active development at MIT right now in my group. And I'll spend a little bit of time talking about Venture, which is our attempt to ask the question, is it possible to build a general purpose probabilistic programming system in which you could maybe implement these other probabilistic programming systems faithfully? But a key feature of all the languages that we've been working on is they're designed to be read and written by both people and machines. And that'll come back again and again throughout the applications. OK, so let's start with Picture, which is a probabilistic programming language for computer vision. So the frame for Picture is to formulate computer vision problems as a kind of inverse to computer graphics. So what do I mean by that? Well, computer graphics is this wonderful success story of computing, which has given us tools for going from symbolic descriptions of scenes. So here I'm showing a source file in the POV-Ray language, which is an open source ray tracer, to images. And the way we go from these source files to images is we kind of parse them and turn them into data structures representing scenes. And then maybe pixel by pixel, at least in the simplest sense, solve an equation which tells us, sort of what's the color of the pixel by simulating all the light bouncing off of all the objects. This is a nasty integral, like evaluating a marginal probability density. It's often done by Monte Carlo techniques. But this can be done on very complex worlds in real time. So there's a very old proposal in visual perception, actually, going back to Helmholtz, that posits that the visual system can be understood as the inverse of optics. So in Picture, what we've been exploring is kind of a computer scientist version of that proposal, which again has a long history in computer vision. So let me give an example. So let's say you wanted to solve the following problem. You're going to be given input images of faces. And you want the machine to be able to answer questions like, how would this face look if you rotated it and lit it differently? So here I'm showing inputs and outputs to a particular picture program. So the input faces are shown here. And then here I'm showing Picture's rendering of a 3D model inferred from that face with novel poses and novel lighting. And here's an example of a face that's not in frontal view. And this column is showing the 3D reconstructions, just so you can kind of get a sense of sort of what the best fit model was to the input data that's then being rotated and re-rendered. So I'm going to use this example to give you a little bit of the mechanics of what one kind of domain-specific probabilistic programming system looks like. So here's an architecture diagram for that application. There's a scene generator, which is this stochastic program that generates random scenes. Those are fed into a differentiable renderer that's actually quite approximate and rough. It doesn't have to produce photorealistic faces. And then those are compared to the image data by this funny differentiable comparator, which I'll give you a little bit more detail on later. And somehow we're going to go from the image data to inferring the scene and then transform it, feed that into a more realistic renderer, and then get back the novel image of what did this face look like. So here's the inference process unfolding. And people asked how long this takes. The default inference algorithm takes tens of seconds, maybe a minute for this application. So it's not suitable for real-time use by any means, but this is the first prototype of the language. So here we're watching inference unfold, slightly accelerated. So you can see how the reconstructions evolve over the course of sampling. So like the initial guess doesn't look very much like the input face, which is shown on the left here. But then pretty quickly it kind of gets into the ballpark, and then it's fine-tuning the model. And that's done by this page of code. So this prototype of Picture is an embedded language in Julia. And there's a scene generator up here, a call to a renderer. All this stuff is built using off-the-shelf components from computer graphics, which are easily available within the Julia environment. And then all the metaprogramming glue to actually construct the inference engine is kind of folded into these calls. You can see here we grab this trace. I'm going to show you more about this stuff later.
But
yeah.
I mean, it seems you have is CNN.
Yeah, I'll show you that in a sec. That's the comparator. So we use deep learning in Picture.
Okay. So it's not just this code. There's a massive other object.
Oh, well, sure. What do I mean? I mean, when I use MATLAB and I write a short matrix times vector, a script that multiplies some matrices, let's say, there's the whole linear algebra subsystem, right? So what I'm trying to highlight is the application-specific code is very small. And the neural net here is not application specific. It's a generic comparator that we use for all the applications in that paper, or I guess the citations on the previous slide. Right, so, and I should say we first prototyped this picture architecture in Venture back in 2013. So we did like a smaller scale version, and then Picture was the domain specific kind of enhancement of it last year. So this scene basically has a mesh, a texture map for the face, and then camera and lighting information. And that corresponds to this code block. It's about 100 parameters. And then the rendering of that in some pose might look like this. And if you ran this whole thing multiple times, you might get a bunch of different faces with a bunch of different orientations and lighting. Now we're going to compare it to the real image by using the latent features produced by a convolutional neural net that's been trained on real images. So this is an optimization. Some of the picture programs work without it. Other picture programs require it. For people who are curious, I can go into the details. The intuition is, if you're building a generative graphics program where the appearance match to the real images is very important, then you don't need this. But if instead you're doing like the poses, where you don't want to have to model all the things somebody could be wearing on their shirt, you need some way of kind of approximately inferring and integrating out your uncertainty over appearance, and that's what the neural net is doing. So unlike the earlier work in Venture, the picture inference engine has a bunch of bells and whistles to make this work efficiently enough. So for example, it doesn't use single site Metropolis Hastings, like Dan mentioned, but it uses a combination of gradient search and elliptical slice sampling, which takes advantage of automatic differentiation to calculate the gradients of various score functions that include the whole renderer. So for people who aren't familiar with automatic differentiation, it's a technique for tractably getting gradients basically through functions that are defined by complex code with data structures and control flow. It's a nice meta program, originally developed in the computational science community. Picture also makes use of learned Helmholtz proposals for fast kind of bottom-up initialization of the scene. So there we're really drawing inspiration from Kinect, Microsoft's Kinect interface. Where one of the core inference engines in Kinect was a set of random forest classifiers that were trained on poses that were generated by graphics software. So they would generate random poses and then train classifiers on the depth data that you could produce by just rendering depth images from those randomly generated scenes. So in the picture paper, we call those Helmholtz proposals. And there's just a simple trick for doing that for a broad class of computation trace structures. That was one of the tricks that was used to make the Kinect real-time. And that's part of the scaling story or the performance engineering story for Picture. So some of our colleagues like Noah Goodman at Stanford and the student Daniel Ritchie have done some really excellent work taking this general framework and also applying it to art, problems in art and graphics. This is one of my favorite examples. So the task here is arrange some cylindrical blocks such that when you light them from the side, it casts a shadow that lines up with this contour. This is, again, like a few hundred dimensional parameter space. So not thousands or millions, but a few hundred. Now the next steps on Picture for us, Picture's being developed in collaboration with Microsoft, including some of the vision, like Pushmeet Kohli, who is one of the vision leads on Kinect, and with David Wingate, who's also speaking here. And we're really focusing on developing a version that's more tightly integrated with Venture and has a runtime in Lua and Terra that's going to be more scalable for work in aerial robotics. So 3D models of scenes that drone cameras can see. Because this feels like a fruitful place to bring structured prior knowledge to bear on interpreting data from the visual world. OK. So that's Picture. Let me just pause for a moment. Any questions about Picture? Yes?
So, the thing you described, it seems like generative adversarial networks are doing very similar things. So have you tried to benchmark with?
Yeah, great question. So, let me reframe slightly. There's a whole class of generative models for images that are being built by the deep learning community. Jeff Hinton's done a few with Russ Solokutinov before generative adversarial networks. Those got more play recently. There have been a few recent papers. In fact, actually, Tejas Kulkarni, the PhD student who did Picture, went to DeepMind after graduation to go work on deep learning for generative image models, to work with Jeff, actually. Well, first Jeff and then off to DeepMind. So a way to think about that is take this architecture, right? This architecture is saying we're going to use human understanding of how to generate images from computer graphics to provide the skeleton of our generative models. And then we're going to use programming technology and technology from computational physics and statistics to take code that represents that understanding and then convert it into code that can do inference. So this is a pretty different approach than trying to directly learn functions that go in reverse. Although you can see, right, in principle, any neural net approach to learning inverses in vision could be posited as alternate paths for implementing this Helmholtz proposal box here. So another way to put it is, at least from our thinking, it's more like those types of research represent ways of developing components that you could integrate into custom inference strategies for picture programs, as opposed to somehow alternative proposals. And actually, part of the project of Picture, I think, over the next few years is going to be to try to argue a question one could ask, right, is, in computer vision, when people are successfully applying deep learning, what's going on in their heads to enable them to come up with the network architecture? So nobody knows, but one class of proposal that I'm interested in is the possibility that you could view some of the successful deep learning architectures for 3D vision as essentially hardware compiled picture programs, where you're using machine learning to just learn very good proposals that simulate the output distribution of some more complex probabilistic program. Any other questions about Picture? Okay, good. So I wanted to spend most of the time in this talk talking about BayesDB, which is a probabilistic programming platform for data analysis that's also the most mature from an applied standpoint. So for example, BayesDB builds on components that were actually commercialized in my first startup, and we just recently, about a year ago, started another startup that's commercializing a product that's inspired by BayesDB. So we have a little clearer idea of how to make it work in practice than we do for some of this other stuff, although it's still early days. So the problem that BayesDB is trying to solve, you can think of like this. So you can start thinking about like this. So in both science and business, empirical inference, so when users have, people have questions they want to answer on the basis of empirical data, there's a consultative workflow that's often used to answer those questions, where a statistician, or in industry these days, somebody with the same skill set who's higher paid, called a data scientist, basically structures and cleans the data, builds models, and then develops apps and predictors. And they're responsible for doing a lot of quality assurance, like on the data itself, but also interfacing with people who can check whether the answers are reasonable and whether end users actually find the resulting systems or answers useful. This process works best when the data is complete, uniform, clean, and cheap. And one of our collaborators at JP Morgan, for example, says a key ingredient is the data scientist has to have a lot of empathy. So they sort of have to be able to understand many different perspectives to succeed at these consulting projects. And we've been doing some applied work in what we call the medium data regime. So not data from uniform processes like click streams, or the outputs of physical sensors, or logs of transactions in the machine economy, but data that comes from non-repeatable events, where you have convenience samples, maybe not random samples, and real-world problems from science and business. And here the data is often sparse, It's not uniform, it's not clean, and it can be very costly to acquire more data. It presents challenges that I think are worth spending a moment on. So the first point, and this is something that I only really began to appreciate by talking to people who did data analysis in business, is that there's actually something of a replication crisis for data analysis. So many of us have heard about a replication crisis in psychology. Let's say some people are arguing that there is one in medicine, but there actually is evidence that there is one in data analysis. So there's a beautiful paper where people actually tried to assess the repeatability of data analysis by fixing the data set in question. So they took a data set of soccer games and a question about racial discrimination in a particular call in soccer. And they had 30 teams internationally try to answer the question. And the results were all over the place. So 20 teams found a statistically significant positive effect, and 9 teams observed a non-significant relationship. And the paper kind of shows like all the confidence intervals for the teams that could report them. So it's pretty grim. And as a result, you actually see at the sort of end user level and the executive level a lot of distrust of data analysis. So there are some recent surveys talking about C-suite executives discounting data analysis they don't understand. And I think it can be tempting, certainly it's tempting to me, given my technical background, to attribute that to maybe like a lack of comfort with quantitative thinking. But I actually don't think that's the case. In fact, it turns out that in life sciences and banking, the CEOs in those industries, which really their existence in their modern form depends crucially on the development of statistics as a discipline. They have the highest distrust in data and analysis. And I actually find that reassuring in a way. Right, so what can we try to do about this from a technological perspective? So let me give an example of the first, I felt kind of maybe meaningful real-world application of BayesDB that led us to start Empirical, which is the new startup. So I was at a Gates Foundation meeting, and I met a clinical researcher working on diabetes. So his goal was to see if you could develop a blood test that you could give, to, let's say, people over 40, that would construct some multivariate proxy for the degree of insulin resistance in the subject. So insulin resistance is normally measured by a painful, costly, time-consuming procedure that requires the person to fast, go to the hospital, then basically get hooked up to a feedback system that fights their body's ability to regulate glucose and insulin. It's painful enough that they're apparently, I gave this talk, I gave this example rather at a data science conference recently, and someone in the audience mentioned that their spouse had received advice on how to fake the results of this test. So like people will exchange that information because it's sort of so uncomfortable, and then also the lifestyle changes you have to enact afterwards are uncomfortable. Right. So if you could improve screening, that would be significant. And so this person I met, Adil from Chalmers University in Sweden, was involved in a clinical trial, a multi-centered clinical trial across Europe, which had produced, among other things, a sample of 250 patients and 400 variables for those patients. 50 of them are clinical indicators, height, weight, blood pressure, this kind of stuff. And then the other 350 were concentration levels of various compounds you can measure from a blood test. So he wanted to see, hey, is there some multivariate proxy for insulin resistance? Oh, and all these patients had undergone this painful procedure via a clinic that was vetted to have high quality, reproducible results. And when I met him, he was actually, he had written this study off as a failure. The stats team had said it was underpowered. It was in the middle of another trial that had 3 times as many patients. And just to calibrate cost of data acquisition, this spreadsheet cost about €6 million to collect the data for. And the follow-on trial was, about 20 million. So it's like, it's a very different regime than the one that, let's say, we hear a lot about at the intersection of machine learning and distributed systems. Where there's some instrumented social process that provides a near infinite stream of data. So the frame for what we did with BayesDB was to kind of use BayesDB as a virtual data analyst. So we can understand what we asked the data analyst to do in English. So we said, all right, BayesDB. So I did this in about half an hour the next day after getting the CSV file. I said, use the data from the CSV file he gave me. And there's a variable, SID1A, which is the ID variable. So please ignore it. And null values in the data are going to be represented by periods. So BayesDB accepts a combination of SQL and various probabilistic languages, which I'll give you some more examples of. So the next thing we said is please build an ensemble of models that might be suitable for exploratory analysis, so like quick and dirty. And use whatever data types you think are reasonable on the basis of the data alone, because I have no understanding of diabetes or the data set. So guess the statistical types for all the variables. Create a meta model using a baseline method called crosscat, which I'll talk more about. Initialize 64 models and analyze for 8 minutes. Then give me a sketch of the probable dependencies between all the variables. And finally, tell me which 15 variables most probably predict insulin resistance. So you spell that in BQL, the Bayesian query language. That's the interface to BayesDB, as estimate the dependence probability of the columns. Call that probability of dependence with M. M's the variable indicating insulin resistance. And order by that variable in descending order, limit 15. So show me the 15 variables where there's the most evidence from the data that there's some predictive information. So it says nothing about the strength, the sign of the relationship, anything like that, just evidence for its presence. And so this is the table we got back. And for me, there was something interesting about it, which was, a lot of the results you can check with common sense. So there's, of course, fasting insulin, fasting glucose, cholesterol, 2 measures of blood pressure, fat mass, body mass index, waist and hip measurement. So things you might expect from a common sense understanding of a metabolic disease that at least in extreme cases has kind of an obvious physiological presentation, at least with some of the side effects.
How come you have these repeating numbers?
Yeah, so that's because we're only using 64 models. And so this is basically discretizing the confidence. Right, so these are Monte Carlo estimates of posterior probabilities in the presence of a dependence. Slightly more formally, they're estimates of the probability that a model-based estimate of the mutual information between those two variables is greater than 0. And what you're seeing is with 64 samples, it's not just the quantization of that posterior estimate. Great question. And it turns out that mannose, which was one of the metabolites that was flagged in this list, my colleague had been arguing for as relevant for giving a prognosis for diabetes for about 5 years on the grounds of mechanistic quantitative models. So from his standpoint, what happened was he gave me a CSV file. I clearly knew nothing about diabetes. And in about half an hour, I was able to repeat back to him some stuff that was validatable by common sense or medical understanding, which correlation would miss in many of these cases, and give him interesting new candidate knowledge, like just hypotheses to look at. So I don't think this proves anything, but this was the first time for me I felt able to go from empirical data about the world to useful knowledge using rigorous methodology. And otherwise my experience learning modeling and statistics has been the more I learn, the harder I find it to trust empirical arguments. Yes?
There is this common knowledge that if you try multiple hypotheses on the same data,
yes,
that's wrong.
Yes.
And there is mathematics that tells
That's
you
right.
when you're right. So are you
Yeah, that's right. I'll talk a little bit about that. And there's a bunch of papers online that go into that question more. 'Cause it's absolutely an essential question for understanding safety for tools like this. So you could ask, the part of it I'll address in this talk is, what's this crosscat baseline method? So the basic idea is we're going to find a way to model high-dimensional data tables And we can't just use something like mixture modeling. So here's a data matrix, and here's the data matrix sorted according to the clusters found by a mixture modeling and clustering algorithm. And one thing you can sort of see is that with mixture modeling, some of the variables maybe turn out to be kind of clean, but then some of them still look pretty noisy. And that's because you're using one set of clusters to explain a whole lot of variables. And probably there are many different ways of looking at the data that would be needed to explain different subsets of variables. So the baseline method in BayesDB is called crosscat. And there's a JMLR paper on it online that has all of the technical details, but the first version of it as a research project in cognitive science goes back to 2006, which addresses this problem. I'm not going to say too much more about it. I'll just say, if you want to get an understanding of the hypothesis space that crosscat's exploring, so in the sense of the traces Dan was showing earlier, if you had a 4x3 data table, what crosscat basically does is it puts down a prior over model structures, like which variables probably depend on each other, and then which cells probably depend on each other for each subset of variables. And it's a semi-parametric Bayesian prior, so it includes edge cases, like every cell in the data has its own idiosyncratic parameter, or there's just a simple set of parametric models that are sufficient to explain the data. And we use standard tools from non-parametric Bayes. So it's like a hierarchical factorial combination of Dirichlet processes is the particular methodology we happen to use to set up a prior over this space. And then inference proceeds by a Monte Carlo scheme that basically shuffles the rows and columns of the data stochastically, exploring this space of model structures, trying to put variables together that appear to have predictive information, and then independently clustering the rows with respect to each group of variables. So one partial answer to your question about multiplicity is there are no tests being performed when you run that query. You've actually built an ensemble of joint probability models. You have a separate question of how safe is that process, but then conditioned on that, you're just querying the models using information theory. So there's actually no multiple testing happening at all. OK, so I'll just say a little bit about another application domain for BayesDB. So let's take a look at a database of satellites. Yes?
So is it, I'm not understanding this obviously, but is it some kind of restricted random walk around graphical model structure that you can impose on your data?
Yeah, that's right. So it's serving the same function as that, but it's not literally using graph structures. So in one sense, you could say Bayesnet structure learning is known to be a difficult problem, both in practice and in theory. Somehow we have to solve a problem that's analogous to that, to go from data to model structures. And the way we're doing it is we're just not literally searching the graph structures. We're searching this kind of induced partitioning of the data, like essentially equivalence classes of graphs in a certain sense.
Do you have measures of how much you trust one part?
Yeah, that's right. That's right. That's right. So the generative, that's right. Yes, good. So so I think I'll skip the satellites example. We've done applications to lots of databases. There are lots of queries you can ask BayesDB, but I'll just show you a slightly more complex probabilistic program than the diabetes example. So I apologize that the screen's getting cut off. I suggest you look at it on the monitors. So here, we're showing how you can build a model that doesn't just use the baselines, this crosscat thing, but actually overrides the models for various variables using standard techniques. So for example, here, we're overriding the generative model for launch mass, dry mass, power and watts, perigee, and apogee in a database of satellites that's public, using factor analysis. And we're exposing the loading factors. And you can also do things like override other variables with regression or random forests to classify orbit type. So we have this interesting hybrid model specified by about a page of probabilistic code that combines the data with domain understanding about statistics and machine learning. But you can go farther and actually integrate Kepler's laws using something that looks more like church. So if you're reasoning about satellites, it might seem natural to put in things we know about orbital mechanics. So you can alter this generative model to plug in a probabilistic program that's written in Venture that actually puts in Kepler's third law and learns a clustering model for the exceptions from Kepler's laws in the data. And that takes about another page of probabilistic code to do. And then once you have that, you have something you can query that's combining the empirical data, the results from statistics, and phenomenological summaries of causal knowledge in the form of the probabilistic program. Okay, and then you can run queries like, I can say infer a variable that tells me the category of how big the exception is from Kepler's laws. So is it a negligible exception with a small deviation from Kepler's laws? Or is it an extremely large exception? So this is a case where I'm now querying an implication of the data and the modeling assumptions that's just not available in the data set itself. And BayesDB gives a framework now for integrating and successively refining modeling assumptions in light of both additional data and additional structured knowledge. Okay. So I'll close by just saying a little bit about Venture. So, and here I'm just really going to give pointers. We're actually teaching a class at MIT, a semester-long introduction to probabilistic programming, and one feature of Venture we're using is the interactive front end, which is there's an embedding into an IPython notebook, but it lets you combine the languages from BayesDB with VentureScript, and in principle, we can integrate other probabilistic languages like Stan or WebPPL. Venture also supports multiple representations of the core objects in probability theory. So not just simulators, samplers like Dan was talking about, but in Venture you can also represent density functions and package them together. So it actually lets you use constructs from programming. So this fixes a limitation of Church, where in Church all random objects were represented as samplers. Here you can represent them using a fuller set of constructs from probability theory. And there's a thesis available online, a master's thesis describing Venture that's the best reference that I would recommend for this audience. And finally, in Venture, inference is programmable. So Dan mentioned this notion of these execution traces, but he was talking about how you'd implement an inference engine for a probabilistic language. Well, in Venture is kind of like a Lisp, but where those traces are a first-class data type. So you can write Venture programs that trace other programs and then modify the traces. And that's the programming model for inference programming that lets us, I think, leave the confines of a purely declarative model that's unlikely to, in my opinion, to scale. Okay, so just to wrap up. I've been talking about probabilistic programming and software. But it's important to realize that, Dan talked about the computability of stochastic inference, right? And Bayesian inference more generally. So for us, in our lab, these software languages fit within the context of a software stack that includes other ideas from systems programming and user interfaces, and a slowly emerging set of proposals for hardware for this kind of computation, and an even more slowly emerging set of proposals for theory and programming knowledge. And there are a bunch of citations on this slide. I'm going to post the slides online for people who are interested in following up. But the question we've been asking ourselves is it possible to construct an end-to-end stack of computing abstractions for this type of computation? And I think there's a reason to want to do this. So the Gates Foundation is trying to use BayesDB ultimately. The aspiration is to use it as a medium for enabling coordination and collaboration by policy advocates, domain experts, field researchers, and statisticians. They all have different types of knowledge that somehow need to be captured in the system. And this is an instance of a kind of applied computer system in which the software is acting as an assistant to a human supervisor. You can imagine this in many different domains. I've shown examples of a few of these in the course of this talk, actually. But where the supervisor is using probabilistic programming, potentially, to give guidelines, questions, and hints, and getting back incomplete solutions with some representation of uncertainty. And supporting this kind of close collaboration between people and software, I think, is going to continually push the capability boundaries of probabilistic programming and may motivate the development of some of the surrounding stack for natively probabilistic computation. Great. Thank you so much.
Thank you. I'm running over time, but if there is one pressing question, maybe we can take one question. Okay, we have plenty of time in the break. Let's resume at 11. So we will start the time of 5.